This is a continuation of the previous chapter in talking about AM, so I will just illustrate a few problems and save the more complex problems for next time. Here once again we have an amplification circuit with a gain of 1000 and we have an input of 20 microvolts with 2 microvolts of noise. First, let's find the signal to noise ratio of the input, which in this case is 20 times the log of 20 microvolts divided by 2 microvolts, which is 20 decibels. Next, let's find the output by saying that voltage output is equal to gain times the voltage of the signal, or 1000 times 20 microvolts for 20 millivolts. All electronic circuits will introduce noise. In this case, the amplifier has a gain of 1000, but it will also introduce 50 microvolts of noise. Let's find the voltage output by saying it's 1000 times 2 microvolts plus 50 microvolts of noise for 2.05 millivolts. The final signal to noise ratio then is 20 times the log of 20 millivolts divided by 2.05 millivolts, and that equals 19.7 decibels. This problem shows that we can measure signal to noise ratio using volts instead of power, and also that we can amplify a signal and somehow reject the noise. To receive an AM signal, we have an antenna to pick up the signal and take the signal to a mixing stage where the signal is mixed with a sine wave from a local oscillator. The idea is that we have a signal coming in at a higher frequency, but then when we mix it with the frequency of the local oscillator, the result will be a lower frequency, which is called the intermediate frequency. And that frequency is chosen by us, the designer. We are looking for a certain frequency which will then be used by the local oscillator. To find that frequency, we take the high frequency coming in, 7.7 megahertz, and add and subtract the intermediate frequency, which is 0.8 megahertz, and then the result is two frequencies, a low one and a high one. Remember, the signals always add and subtract. Usually the higher frequency is taken and used by the local oscillator, then the high frequency coming in subtracted, and the result is the intermediate frequency. Then the frequency that's not used, the lower one, is filtered out with a series of filters. Usually the local oscillator circuit includes a manual variable capacitor, which is called a tuning capacitor. In the case of electronic tuning, the manual variable capacitor is replaced with a varactor, and a varactor is a diode which also contains some internal capacitance which can be changed. This capacitance can be changed with a DC level or an audio signal. But if the capacitance can be changed, that means that the resonant frequency will also change. We have a formula for the varactor which relates the new frequency, the original frequency, the original capacitance, and the new capacitance. Let's say we have a circuit with a varactor, and the varactor has a value of 100 picofarads plus or minus 10%, and that the varactor circuit is putting out a frequency of 5 megahertz. Now let's take a DC level or an audio level and change the capacitance by 10% downwards, so the new capacitance will be 90 picofarads. And then the original frequency was 5 megahertz. Now we want to solve for the new frequency. We rearrange the formula to solve for the new frequency, and it's 5 megahertz times the square root of 100 picofarads divided by the square root of 90 picofarads, and the result is 5.27 megahertz. In other words, we can change the local oscillator up and down depending on how we change the capacitance of the varactor. The varactor is often used in FM receivers where the frequencies are much higher, and therefore the small changes of the capacitance in the varactor will affect the higher frequencies.